So would you please make very, very welcome for a Monday afternoon, all the way from just up the road in Canberra, Professor Andrew Stuchbery.
Thank you, Chris. Thank you. It's a real pleasure to be here. Talking about nuclear power inevitably in this country involves a debate, a political debate and a public opinion debate. But this is an international science school, so I would like to put an emphasis on the science in the two lectures that I give to you this afternoon and then again tomorrow morning. So I'm not really going to talk to you about my own area of research, which is studying the quantum mechanics of the nucleus and measuring its magnetic fields, but I will talk to you about nuclear physics behind nuclear power, and I'll talk to you about how reactors work, how the current reactors work, and about people's ideas and plans for the future. And I'll even stare a little bit into the crystal ball, which is a very dangerous thing, and perhaps make a few personal opinions about the way things might go. So at the moment, about 11% of the world's electricity is generated by nuclear fission. I want to talk about, as I said, how it works and what the future might hold. This is a picture of a new Westinghouse AP1000 reactor that's just about to come online in China. There was a news article that it was commissioned on the 1st of July. I don't think that means connected to the grid, but that will be coming soon. At the moment, there's about 440 reactors worldwide, generating not quite, about 380, almost 400 gigawatts electrical, 32 countries. Most of them historically, United States, Europe, and Japan. If we look at where things are happening, where there's new build, in the established countries, there's some new work on replacing reactors, although it's not very aggressive. The real growth is in China. Huge new build of reactors in China. Two interesting cases in yellow are Belarus and the United Arab Emirates, UAE. These two countries are non-nuclear countries. They don't have any previous nuclear, but they are building reactors. Belarus is interesting. Their motivation is that they want energy security. That's often a motivation for going nuclear. They don't want to be dependent on importing Russian gas. This is a kind of energy security is a typical reason for going nuclear. But what's very interesting about that country is that they copped probably the worst of the fallout from the Chernobyl disaster. And I would have thought that perhaps that would be a country that would be staunchly anti-nuclear, but apparently not. Our own region in Asia, there's a lot of activity, and again, China is building a lot of reactors. They're planning to just about double their capacity in the next few years. At that point, they'll have a reactor fleet and an amount of electricity production that's about the same as France. It's not as much as the United States, which at the moment is the biggest nuclear power producer, although it's not the biggest in terms of the fraction of their electricity. So that's by way of introduction and context. Where I want to go with today's lecture is I first of all want to make sure that you know some reactor terminology and some nuclear physics terminology. I'm going to give you a short history of nuclear power, starting from the beginning of nuclear power. We'll talk more about developments next lecture. Then I want to start explaining how reactors work. So today the emphasis is going to be on the nuclear physics. Tomorrow I'll talk more about how reactors work, and that will be more on the reactor design and how that part works. I'm going to flash up some pros and cons of nuclear power. I'm not going to specifically elaborate them at that point. I will have touched on some of the pros and cons as we talk. And then at the end of today's lecture, I want to give a few more details on the demographics and the statistics, expanding a little bit on what I just showed you. Tomorrow's lecture, we'll talk about, as well as more physics of reactors and alternative reactor technologies. I'll talk about accidents and safety strategies tomorrow, about waste management, and then I'll end up on the pros and cons, and we can discuss those as you see fit. So let's start off. How do we name nuclei? Well, we say the element and we give its mass number. So here's the example of lithium-7, stylized picture of a lithium atom. It's the third element in the periodic table. It's got 3 protons, 7 nucleons, 7 protons plus neutrons. Now, once you say it's lithium-7, if you've memorised your periodic table, you know how many protons and neutrons, provided you know your periodic table and you can do a subtraction. But I'm not very good at doing that, particularly when I'm trying to say words. So often nuclear physicists will write down, over-specify. So the Z is the atomic number, determines which element. N determines which isotope, and the mass is the mass number. It's close to the atomic mass in atomic mass units. The other thing we need to be a little bit familiar with is the chart of the nuclides. Now, the chart of the nuclides is simpler in many respects than the periodic table because nuclei don't have simple, I'm going to say this is radical for a chemist, but they don't have the same kind of simple periodicity that you get in the chemical elements. So we do something a bit dumber for the chart of the nuclides. We just start at the bottom with a neutron and a proton, and we put the elements, the Z numbers, up the page. Each box is an individual nuclide, and then the horizontal guys are the isotopes. They've got the same number of protons but different numbers of neutrons, and as we go up this way we add protons. So the horizontal lines are the same Z, the same element, they're isotopes, and then upwards it's the same number of neutrons, they're called isotones with an in it. And then the other thing that is relevant here is that the constant mass number goes on the diagonal, and that's relevant because that's the path of beta decay, and we'll talk a little bit about beta decay as we go. All right, a reactor schematic. This is a very dumbed down schematic of a reactor. All the action, the interesting stuff happens here in the core. The core contains fuel. That's represented by these red lines. The fuel is plutonium, uranium usually, and sometimes plutonium usually. It contains a moderator for a thermal reactor. We'll mostly talk about thermal reactors today. I'll explain what that means later. There'll be control rods to control the reaction in the core, and there'll be a coolant that keeps the core cool. That's one purpose, but the main purpose is to get the heat out so that you can use that to generate electricity. Then you have some kind of a steam circuit, and it goes off to a steam turbine, and it's just the same as a coal-fired plant or a gas-fired plant. Okay, the next slide says all that I just told you. I didn't mention the reflector. That's just material to help keep neutrons in the core, so we don't need to go through that. Oh, yes, we do. On the next, no. There's fissile and fertile material. I'll explain that in a moment. Okay, neutron-induced fission. There's a little cartoon up here. They're never quite right, but it gives you the idea. You have a neutron hit typically a nucleus of uranium-235. In fact, even if the neutron just drifts in and hits the nucleus and captures, it will induce a... sorry, I bumped the thing. with the hand gestures. Yeah, so the neutron doesn't have to fly in. Even if it just comes into contact with the uranium-235 nucleus, it will induce a fission. The nucleus starts out being Australian rules football, rugby ball shape, and the fission process involves this necking and then splitting into two. Now, after it splits into two, these fission fragments are hot, they're neutron-rich, and they spit out a couple of neutrons. This whole process takes about 10 to the minus 20 seconds. So, bing, it's pretty fast. Chain reaction. So the idea of the chain reaction is you have a neutron, it induces a fission, you get fission fragments, the nucleus breaks in two, emits another couple of neutrons, which in turn induce fissions, and this process multiplies exponentially, and if that happens, you have a bomb. We don't want a bomb. We want a controlled reaction. It's interesting. The discovery of fission was reported in February 1939. By May 1939, there was a patent for nuclear energy, Leo Szilard. Okay, fissile and fertile. Uranium-235, odd mass uranium isotope. It's 0.7% of the uranium we dig out of the ground. The other 99.3% of the uranium we dig out of the ground is uranium-238, even mass. This one is the only one that's fissile. What that means is this is the only one that if you introduce a neutron to it, at thermal energies, it will fission. The uranium-238 won't. You can't make a reactor, or a bomb for that matter, out of pure uranium-238. This is the only one. Okay? But what you can do is, and this happens in a reactor, you can capture neutrons on uranium-238, make it into uranium-239, so this is a neutron capture, then this nucleus is unstable to beta decay. It changes neutrons into protons in two steps and makes plutonium-239. This stuff has a half-life of about 20,000 years, so it's effectively stable. So what you can do is you can take this fertile material, uranium-238, and make it fissile. Now, during the Manhattan Project, when the objective was to build a bomb, and we won't go into that, but you've got two choices. This stuff is only 0.7% abundant, and its mass differs by only of the order of 1% from uranium-238. You can't separate it chemically. It's hard work separating the fissile isotope. So the idea was, do we work hard and enrich this, or do we make plutonium by taking this fertile material, doing this process which can then be separated chemically? So that's the history there, and in the end, as you probably know, they did both. All right, so a short history of nuclear power. The first controlled reaction, 2nd December 1942. CP1, Chicago Pile 1. And it really literally was a pile of graphite and uranium in any form that they could get hold of. Went critical on the 2nd of December 1942. If you look on the internet, you can find this plaque. It says it's the first nuclear reactor, the world's first. Actually, it's not true. It's not the world's first nuclear reactor. The world's first nuclear reactor, there was at least 15 of them, were here 2 billion years ago in uranium deposits. The ones that have been found are in Oklo, this uranium deposit in Africa. Now, the half-life of uranium-235 is about 0.7 billion years. 2 billion years ago is about 3 half-lives ago, so the amount of uranium-235 then would have been 2 times 2 times 2, 8 times what it is now, around about 5.6%, which is about the same as in a modern power reactor. So what happened was that this uranium deposit formed, and water would trickle in, moderate the neutrons, it would go critical, get hot, boil the water off, no moderation, turn itself off, cool down, water trickles back in, process repeats. So these things sat there, self-controlled reactors, turning themselves off and on for a couple of 100,000 years. Okay, let's jump forward back to the present century. After the Chicago piles, there was this X-10 reactor at Oak Ridge National Lab, and I just found my first typo. This is a graphite core reactor. It was used for research well into the 1960s. It's still there, but it's now a national monument. My connection with this reactor is that one of my PhD examiners worked on this device before he started doing accelerator physics. Now this starts to develop the technology. This is still air-cooled. It's only 100 kilowatts. That's really not much power. But the fuel now is metallic uranium jacketed in aluminium. Okay, so during the war and the Manhattan Project, the objective was to make plutonium. So reactors were built at this Hanford site on the Columbia River. These were water-cooled, graphite-moderated reactors. They first went critical in September 1944, and the purpose of these reactors was to make plutonium. Here's a picture of the first gram-sized piece of plutonium made. Okay, we know then the war happened and so forth. After the war, there was an Atoms for Peace initiative, and the idea was, let's go for nuclear energy. So the first nuclear electricity generated was December 1951 in an experimental breeder reactor. It lit these 4 light bulbs, and really that was the beginning. This is a fast reactor. We'll talk about what fast and slow reactors are later on. So the idea here was to breed plutonium-239 from uranium-238. It'll come up again and again. In the early days, it was thought that uranium wasn't very abundant on Earth, and it was felt that we really needed to breed plutonium in order to sustain nuclear energy. Turns out that uranium is a lot more abundant than we thought. In fact, Australia is sitting on the biggest known uranium reserves in the world. And so this motivation for breeding reactors has waned. The first real nuclear power plant was in the United Kingdom. These were graphite-moderated, gas-cooled reactors, and here's Her Majesty turning this thing on in 1956. All right. Now, most of the nuclear energy today is in the United States, and most of the reactors in the world are pressurized water reactors, pressurized light water reactors. They have their origin in submarine and naval engines. They were reactors designed for naval propulsion. So the idea is a compact, safe reactor, closed, high-pressure circuit, steam generator, secondary circuit, and the first nuclear submarine, USS Nautilus, launched in January 1955. So the submarine engine became a pressurised water reactor with a view to commercial electricity production. There was the development of these boiling water reactors, which are really a variation on the pressurised water reactor little bit simpler. The difference is that this one doesn't have a secondary steam circuit. The consequence is there's some difference in the internal structure. Both reactors produce similar temperatures of steam to the steam turbine. They have similar thermal efficiencies. So the thermal efficiency of a nuclear power plant is in the 30% range. So what this means is that if you see a power level gigawatts electrical, that's the electrical power produced by the plant. If it says gigawatts thermal, that's actually the thermal heat power that you have to produce. And the thermal power will typically be 3 times what the electrical power will be. This is a little bit more realistic picture of a pressurized water reactor. They always have these containment vessels that are set up well, really as a barrier in the case of a failure. I showed on the first slide this Chinese reactor. This is a picture taken in September 2011 of the pressure vessel going into the reactor. It's interesting here, this thing is 4.5 metres in diameter. It's not really that big, and 12 metres high. I wanted to show you a fuel assembly. The fuel pellets, the pellets that have the uranium in them, are about the size of the top of your finger. These are stacked in fuel rods, which have a diameter of about 1 centimetre. Those fuel rods are then stacked in these assemblies, and there's control rods go in between them, and then this whole thing sits vertically in the reactor. That's light water reactors. Heavy water reactors use deuterium instead of light water. The motivation for using heavy water instead of light water is that you can't actually make a light water reactor with natural uranium. You have to enrich. And in the early days, not everybody had access to enrichment technology, and it was hard. So early reactors were often designed to run on natural uranium. And to do that, you have to choose the moderator properly. We'll talk about that in more detail tomorrow. So you can use natural uranium, and the Canadians developed these heavy water reactors. You can see it's much bigger. Here's a person, and here's the pressure vessel, or the reactor vessel. It's called a calandria. It's much bigger, largely because of the moderating properties of the heavy water, the deuterated water, compared with light water. Now, 3 Mile Island. Who's heard of 3 Mile Island? Nuclear accident in 1979. We'll talk about it in more detail tomorrow. Had a huge impact on the nuclear industry. In the United States, virtually all the ordered reactors after 3 Mile Island were cancelled. A number that had started building were put into service. What do you think happened to nuclear electricity production after that accident and the cancelling of the new build of reactors? Amazingly, went up. So this is the capacity factor. So this is the amount of time you're producing electricity for the amount of real time. Capacity factor went up to the 90% level. Sorry. And the amount of electricity produced, this is a log scale, went up by nearly a factor of 3. So this accident was a huge wake-up call to the nuclear industry, and one of the outcomes is not only safer operation, but better operation. Fukushima accident, you must have heard of that, I guess, because it only happened a couple of years ago. Rightly, worldwide, construction essentially stopped, halted after the Fukushima accident. People reviewed their safety cases, thought very hard, and now construction has started again. So when we talk about nuclear power, we talk about different generations, starting with these early experimental reactors that I've talked about, the pressurised water reactors, the boiling water reactors, the CANDUs, advanced reactors of generation 3, the ones that we're seeing go in at the moment, like this AP1000 in China, considered generation 3 plus. They're considered evolutionary designs. And then people are dreaming, I don't know how they came up with this pyramid and the light, but people are dreaming about revolutionary designs for the future. All right, I want to talk about some nuclear physics now, real physics. This is not just pictures of reactors and history lessons, but it's physics. Always with an allusion to the Big Bang Theory. So what do nuclei look like? Well, for our purposes for the moment, we can think of them as like a bag of marbles with the protons and neutrons stacked in, more or less touching each other. The reason we think of them like that is because the radius of the nucleus is proportional to the cube root of the number of nucleons in the nucleus. In other words, the volume of the nucleus is proportional to the number of nucleons in the nucleus. So if you bung another one in, then the volume goes up by the amount you just stuffed in. We know that from electron scattering. So Robert Hofstadter, not Leonard, got the Nobel Prize for that in 1961. Now, so we know that the nuclear force must be attractive. It must be short range because it doesn't appear very much outside the nucleus. It must stop the nucleons from, they must push against each other at some level. And it must overcome the fact that the protons are positively charged and trying to push the nucleus apart. So we know that. Now, like all of these pictures, they're always a bit of a lie. And whenever anybody introduces some new concept to you, they always dumb it down and only tell you half the truth. And I've done that here. Because in fact, most nuclei are not spherical. Most are shaped not like a soccer ball, but like, well, I come from Melbourne, so an Aussie rules football, right? And in fact, our fissile isotopes are shaped more like this than a round circle. So here's the chart of the nuclides. Overall, these are known nuclides. There's a couple of thousand of them. We believe that there's a few thousand more that we haven't made on Earth yet. They occur typically during supernova explosions. Our fissile isotopes are up here, high Z, right at the limits of the nuclear chart. In the centre of these regions, well, there's closed shells. I'll tell you more about closed shells. Nuclei have shell structure like atoms. So these are analogous to the noble gases. So the nuclei near closed shells tend to be spherical, but the ones away from closed shells, which is most of the nuclei, are deformed. Okay, next thing. We need Albert Einstein. We need equals mc squared. I'm just going to take it as a given that energy and mass are equivalent. An atomic mass unit is equivalent to about 1 GeV, 1,000 million electron volts. Everybody happy with me talking about electron volts as a unit of energy? Yeah? Good, good. So I showed you the nuclear chart in 2 dimensions. We actually think of it in 3, and we put a measurement of the mass or the stability on the vertical axis, and we end up with this valley that we call the valley of stability. So this plot shows the mass excess, which is the difference between the actual mass that you measure in a mass spectrometer and the mass number, the number of nucleons, times c squared. Okay, so if we look at the nuclear chart, up the centre of the chart, there's a region that's usually shown in a darker colour. It represents the stable isotopes. These are the ones that we find in nature. The ones to the right and the left, if they're on this side, they're proton-rich, and they decay by positron emission. They emit positive electrons, positrons, to change protons into neutrons, and they head down this valley to the bottom of the valley to stability. Similarly, on the neutron-rich side, over here, they convert neutrons into protons by emitting electrons, and again make their way down to the bottom of the valley. Now observe something else here. For very light nuclei, they like to have equal numbers of protons and neutrons. But as you go up the nuclear chart, the stable nuclei put in more and more neutrons. So this thing curls over. Now why do you think that would be? Why do you need more neutrons, extra neutrons, as you put in more protons? Exactly right. Good. At least somebody's awake. Okay, good. Yes. So this is a consequence of the fact that the protons are trying to push the nucleus apart. You put in extra neutrons, that adds nuclear force that dilutes out the Coulomb force. This is a kind of three-dimensional view along the valley of stability. Down in this hole here, you can't see it, is oxygen-16. It's one of these doubly magic nuclei, closed shell for protons and neutrons, which gives it extra stability. So it's down in that hole there. And then you have neutron-rich guys over here and proton-rich guys over here. All right, now, binding energy per nucleon. This is the curve. Did you see this last week when you heard about fission? Yeah, okay. So I can probably skip over it. So this is the binding energy per nucleon for nuclei. So the binding energy is the difference in the mass of the nucleus, between the mass of the nucleus and the mass of the sum of its parts, multiplied by c squared. And I've worked the numbers here through for iron-58. The iron-58 nucleus weighs about half an atomic mass unit, or 500 MeV in total binding energy, less than its constituents. So this mass disappears and becomes energy. Okay. This is how stars burn. They turn nuclear energy into binding energy and generate kinetic energy. So if we look at this curve, there's some funky stuff going on here due to shell structure and clustering. There's an average binding energy of about 8 million electron volts per mass number. There's a steep rise at low energies due to surface effects. This is where you do nuclear fusion. Then there's this slow decrease for high Z, which is coming from the Coulomb force trying to push the nuclei apart. So we can do fusion or we can do fission. Now let's put a benchmark on some of these things. Let's say we're burning methane. We burn a methane molecule and you get about 8 EV per methane molecule, which turns into 50 kilojoules per gram. So that's just a benchmark, reference point. Nuclear fusion, you get about 340 gigajoules per gram if you do D plus T fusion. That's a lot more than the chemical energy. For the nuclear fission, you get about 80 gigajoules per gram. It's less than fusion, but it's a technology that we have working now. And if you work out this problem of what's the potential energy of, say, one fission fragment next to another, and they repel each other, that energy is very close to the energy you get out from a nuclear fission. So if you're talking nuclear fission, it's not really nuclear energy, after all. It's actually still Coulomb energy. It's Coulomb energy coming from the nucleus. So what happens is we split these heavy nuclei. This shell structure, this extra stability near tin 132 here, means that a lot of the fission fragments end up with masses near here, and that by default means that the other fragment has to end up over here. So you get a high mass group and a low mass group. There's about 200 MeV per fission recovered. Most of it is in the kinetic energy of the fission fragments, which then goes directly into heating up the fuel pellet. There's kinetic energy of neutrons, gamma rays, and then the fission fragments themselves, they also undergo radioactive decay. In fact, this radioactive decay of the fission fragments was what was behind the Fukushima accident. So, now, delayed neutrons. What are delayed neutrons and how do they help? I'll come back to that in a moment. What about the neutrons that come out? If you thermal fission uranium, you get about 2.5 neutrons per fission on average. Sometimes it's 2, sometimes it's 3, so on average 2.5. Plutonium, it's closer to 3. And their distribution of energies is like the molecules in a gas, but this temperature is something like 1 billion degrees. Its average energy is of the order of 1 million electron volts. The delayed neutrons, the neutrons are actually coming out of the fission fragments. If you find a cartoon movie of fission online, it's likely to show the neutrons coming out as part of the fission process. Whereas in reality it doesn't. The nucleus splits into the two fission fragments, but then the fission fragments are themselves what emit the neutrons. Now some of these fission fragments don't immediately emit neutrons. What they do is they beta decay, but they can beta decay into a high excited state of the daughter, which does emit neutrons. Remember that the average binding energy per nucleon is about 8 MeV. So if this excited state is relatively high in the nucleus, there's a good chance that the neutron will just dribble out. So these are only about 1% of the neutrons that come out of fission, but they're critical for controlling reactors. How much fuel do you need to generate a gigawatt electrical? Well, it's just it's a tiny amount compared with the amount of coal because of the energy density. And this is one reason that countries opt for nuclear power. If you don't have big coal reserves, a few tons of uranium will supply your electricity for a year. And the waste, we hear about nuclear waste being an unsolved problem, which is not true, I believe. The volume of nuclear waste is actually quite small. I think most people don't realise it, but you burn coal, there's traces of radioactive elements like uranium in coal. And so burning coal puts tons of uranium into the environment. Okay. Pros and cons of nuclear power. We're actually doing okay for time. So now, I don't consider myself pro-nuclear. I guess I'm anti-nuclear. I think we should have a evidence-based discussion. But for me, one of the big pros for nuclear power is climate change. It's a technology that can generate a lot of power, a lot of electricity, with essentially no greenhouse gas emission, and it works. So if we talk pros and cons, there's different aspects. There's the technical, science and engineering. That's probably the main concern for people working on these evolutionary generation 4 reactors. There are often science and engineering problems that are yet to be solved. There are alternatives, pros and cons. What choices do we have? Are we choosing between nuclear and coal or nuclear and renewables? There's economics. Is what we want to do economical? Is it costed appropriately? And then, of course, there's the politics, stroke policy, and social science or social license, which is a big factor. There's a quote here: "I've never seen a credible scenario for reducing CO2 emissions that did not include nuclear energy." Other people have made quotes like, "Trying to fight climate change without considering nuclear energy is like trying to fight with one arm tied behind your back." So I want to try to give you a little bit of an idea of why people might make those kind of statements. Now, here's a case of looking into the future, and it's done by Mobil Exxon. I'm not sure whether we should entirely trust them, but it doesn't really matter who does this analysis. If you sort of squint and don't look at the real numbers, the basic story is going to be the same, whoever does it. And that indicates that as we go through the next few decades, if developing countries are going to continue to develop, if the world is going to get to be a better place, a healthier place, we are going to need more energy. And how are we going to do it? Well, we're facing climate change, so we've got to cut these fossil fuel energy generation methods. And nuclear can play a part in this, along with renewables. It might be better if you reattach that.
Back on.
You can edit this out afterwards, or everybody can laugh.
That never happened.
Nobody laughs. Okay. Now, there's actually hard evidence that nuclear has replaced fossil fuels in the period from 1973 to 2013. The amount of nuclear worldwide went up from a bit over 1% to almost 10%, and that shows here as a direct cut in oil in particular, but also there appears to be some impact on coal, but particularly oil, fossil fuel. CO2 emissions by country. So this is just total emissions, not emissions per capita. Well, this is per capita, this is per person. This is total emissions by country. China at the moment is the biggest, United States second, and down we go. Over here it's per capita. You can see that CO2 emissions depend on a number of complicated factors. It depends on the population of the country. It depends on their GDP, their gross domestic product. It depends on other factors. If you look at the statistics for CO2 emissions overall in Australia, I think there has been some decrease recently. Part of that is because we're not smelting as much steel, we're not doing as much aluminium smeltering, and we're not doing as much cement production. We've moved that overseas to Asia. So it's not just electricity production that goes in here. There are some CO2 intensive industries that contribute to these data. So Australia's a long way down here worldwide, but on the per capita, we're among the worst. In fact, we probably are the worst for electricity generation. Now, I made this, excuse me, I made this graph up last week, and found it hard to get CO2 data that was current with the nuclear electricity percentage. So I wouldn't take a lot of notice of where these numbers for Japan and Germany in particular are, because they've been moving around post-Fukushima. But you can see that the trend is that if a country has more nuclear electricity, it tends to have less CO2 emissions. Now, to evaluate that effect, you really need to take into a lot more complicated factors, which is kind of a social science thing. But here's one case study of Sweden looking at the effect of nuclear power emissions per capita as a function of gross domestic product. And according to this analysis, the CO2 emissions are about halved by Sweden's use of nuclear energy compared with coal. So I'm just going to make a list of pros and then a list of cons. Pros: it's almost zero CO2, high energy density, energy security, it's baseload power, it's a proven technology that works now. The plant footprint is fairly small. You saw that a reactor vessel is just a few metres in diameter. A reactor building is not a huge plant. It's conventional generation. It plugs into the existing grid. It would replace coal plants, and it wouldn't cause the phase problems which contributed to the blackouts that we had in South Australia recently. It's actually a small fuel cost. The cost of the uranium to put in the reactor is not that high. There's a small waste volume for which technical solutions exist. And perhaps it might surprise you, but it's safe. There's actually a good safety record overall. And new plants will be safer and more efficient than the current ones. Now, I'm not going to try to justify all of those right now, but we'll discuss them more as we go. The cons against, well, I think particularly in Australia, the con is social licence and public perceptions. The view of the general public on safety and waste management is diametrically opposed to that of experts. There's a huge upfront cost for plant. Nobody's going to invest in an expensive plant if there's a change of government that then says, no, we're not going to go nuclear. You need special nuclear governance requirements. You've got to regulate, you've got to ensure safety, security and safeguards. So safety is making sure that people are safe, not just the workers but the public who are in a community with a nuclear power plant. Security is making sure that nuclear material doesn't get into the wrong hands. So we're thinking criminals, terrorists. And safeguards is ensuring that nuclear weapons aren't made. The players here are more likely to be states that divert material from nuclear power into building nuclear weapons. On that point, it has to be admitted that there is a historic link between nuclear power and nuclear weapons. It'll be interesting to see how that goes ahead. One of the new countries making nuclear power was UAE, United Arab Emirates. They're actually doing everything by the book, by best practice standards of the International Atomic Energy Agency. And this might be one case where there isn't a link between nuclear power and nuclear weapons. We'll have to see how that plays out. And in Australia, it's currently illegal. We can't have nuclear power until the law changes. All right, a little bit about demographics, statistics and forward projection, and we can come back and we will talk a little bit more. I'll put a little bit more flesh around those questions of pros and cons tomorrow. So I showed this slide at the start, 440 reactors, about 11% of the world's electricity worldwide. How does that shape up in detail? Well, as I've indicated, there's nearly 300 pressurised water reactors. This is the most popular kind of reactor. I think it will probably continue to be the most popular kind of reactor. United States, France, Japan, Russia, China. The next most common is boiling water reactor. There's a lot in the United States, Japan, Sweden, Taiwan. I'm not sure why they're not listed here. There's the heavy water reactors. Canadian heavy water reactor, CANDU. India has these reactors. One of the disadvantages of this CANDU reactor is it uses natural uranium and it has what's called on-load refueling. You can put fuel through that thing all the time. So that's all right for continuous electricity supply, but it also means that you've got access to put uranium in and make it into plutonium. So CANDU reactors are not a good reactor from the point of view of proliferation risk. Gas-cooled reactors, graphite moderated gas-cooled reactors in the United Kingdom, there's 14. These are starting to be closed down. I haven't talked about gas-cooled reactors. We'll look at them when we talk about Generation 4. And fast neutron reactors, there's a few experimental reactors around the world, but Russia has about 3 of these putting electricity into the grid. There was one at Dounreay in Scotland that operated for 20 or 30 years, a fast reactor, fairly small one. So looking to the future, this is the picture that you find if you look up Generation 4. We're starting to sit at this Generation 3 plus level. These advanced reactors are starting to, the aim is for greater safety. There's a tendency for them to be big baseload power machines. And this AP1000 in China is a classic example of these Generation 3 plus reactors. So just a little bit more detail on this. Compared with a conventional pressurised water reactor, this one is designed, it's got this convection tank on top. The idea of this reactor is if you have a reactor trip and you lose off-site power, this thing will just sit there and look after itself. You don't have to intervene, at least for 72 hours. Reduced complexity. So the idea is to simplify the system. You don't have to have as many safety valves. It'll take after itself. You don't have to have the risk of safety components failing. Reduced piping, and so forth. So it'll be interesting to see how these reactors perform over the coming decades. A little bit of staring into the crystal ball and the future. This is an example for France. What we're finding is that people are extending the lifetime of their current plants. So there's a lot of there's a lot of experience with running the reactors. They were perhaps considered when they were built that they might be turned off by now, but regulators are looking carefully at what's happening, and in many cases there are options for lifetime extension. At the same time, the Europeans are developing this European pressurised water reactor. It's almost the opposite philosophy from the AP1000, which has these passive systems. This one's well, I was going to say an engineer's dream. Everything's engineered to the hilt, multiple safety systems. And then they see generation 4 reactors, these new generation reactors coming into play perhaps maybe 2030 to 2050. I'll talk more about fast reactors and what they are and how they work tomorrow. For the moment, I think one other thing. This is important for Australia before I finish up. Small modular reactors. So what I've been saying so far is most of what's actually been happening in China is big power to produce electricity for thousands of households. At the same time, there's a lot of research going into what are called small modular reactors. So instead of designing bigger and bigger, we're starting to go smaller and smaller again. And we're going back to the scales of some of the earlier experimental reactors. But the idea is that you now make a modular design. You have a reactor that'll basically fit on a truck. So the idea then is that you can modularize your nuclear electricity production. If you're in a remote region far from the grid, you might be able to put in a small reactor to generate electricity. So this is just a pretty picture to indicate there's a lot of light water reactor, cooled small modular reactors. The idea of the modularity too is that you don't have this high upfront cost for the plant. It's not as high. You can start off with something small. You can start generating electricity. You can sell it. You can start to pay for this thing while you're investing for the next module and then build up modules gradually. A lot of activity around the world in this area. People are also looking at small fast reactors, small modular fast reactors, and there are a number of prototypes. So I've talked about these advantages. I think I said most of them. I think where this is at the moment is on one side there's a question of demand, and then on the other side there's the what's the word? It's the licensing process with the regulator. We've got to make sure that the safety systems and all of these things associated with safety and security are in place for these small plants. So the future, in my view, and I'll come back to this again at the end of the lecture tomorrow, so there's probably a few things here that are assertions without any obvious basis in what I've said today. I think advanced pressurised water technology, this is the technology that started out as a submarine engine. It's a fantastic technology. We've got many decades of experience. It's the most popular reactor type in the world today. And I think it will remain the dominant reactor type for the immediate future. There's nothing wrong with boiling water reactors, but it just so happens that the Fukushima accident was with a boiling water reactor. So that then creates a little bit of a psychological barrier. I think small modular reactors could play a role in producing nuclear power to Australia if there's a need for it, if there's community support, if many ifs. But I think it would be a sensible path to take if we went that direction. Fast reactors, I'm promising to talk about them tomorrow. They have a role in radioactive waste management, and we'll discuss that further tomorrow. The Generation 4 reactors, they're being designed not just to produce electricity, but also to produce process heat. They're looking at desalination. Water is going to become a commodity that some people worry that the wars are going to be over water in future. Desalination is going to be important. Hydrogen production is going to be important. Process heat. Some of these Generation 4 reactors could be game changers beyond 2040. Okay, you're not going to generate process heat, for example, so readily with renewables. People talk about thorium-uranium cycles. I think our reactors are going to be using uranium and plutonium, at least the ones that are making electricity, for the foreseeable future. But depending on how things go and how successful we are with meeting our energy needs and other needs with renewables, eventually thorium-uranium cycles might play a role. People also talk about accelerator-driven systems. So this is a system where you have an accelerator initiating nuclear fission instead of neutrons. One of my former students who now works for the International Atomic Energy Agency says, oh yeah, these are great. These are an employment opportunity for physicists. And full stop. But I think they won't be energy driving systems anytime soon, but they'll continue to be exciting research devices. And at that point, I'll finish and we can take some questions. And I even did it on time.